Our next speaker is Dr. Valerie Brown. Dr. Brown is a professor of pediatrics in the Division of Pediatric Hematology Oncology and Stem Cell Transplant at Penn State University at Hershey Medical Center. She received her bachelor's degree at MIT and PhD and MD at the University of Pennsylvania Perelman School of Medicine. She also did her residency and fellowship at CHOP. She serves on numerous committees and boards related to neuroblastoma and other childhood cancers. She instituted and leads the clinical program, experimental therapeutics, research, and clinical team. She has lectured at many programs throughout the country as well, and her talk today is on the current trials at BEAT-NB. Dr. Valerie Brown.
Okay, let me see. First of all, let me get this thing working. I'm notorious for hitting the mic with a hand that starts to flail because I tend to get overexcited because I love science and I love medicine. So much so, just as a quick story, when I had a lab when I was back at CHOP. And by the way, I'm not a neuroblastoma expert. You're like, why the hell is she even here if she's not? But Giselle Scholler, who's the leader of the Beat Childhood Cancer Research Consortium, was unable to attend. And she actually asked me if I would step in her place to give you updates about our consortium, to which I'm a member. But this was back at CHOP, so this was over 10, 15 years ago. My nephew, who now is a resident in pediatrics and genetics at Cincinnati Children's, was working in the lab over the summer, and I had in my office, he was there, one of the technicians was there, and we were talking about one of the pathways we were studying in leukemia, and I was getting really very excited, and I just blurted out, "Don't you just love science?" Like that. And I thought they would respond like, "Yeah, we love it too." That's not how they responded. They looked at me like I was crazy, and it was just dead silence in my office. And I'm like, okay, and they're like, yeah, I guess we love it. Maybe not as much as you do, you know. Next thing I know, I walked up into the lab a few hours later. Wouldn't you know it on the whiteboard? It says, in quotes, "Don't you love science, Val Brown." And that lived in there forever. So I apologize if I get very excited, but this is just something I just think is, in general, is just so fascinating. And remember, data don't lie. People may misinterpret data, but the data are the data. And that was just a tenet I was raised on professionally. And despite being at CHOP for training there and being there as an attending in their blood and marrow and cellular therapy program, I wasn't really part of the neuroblastoma team, but I certainly felt like it because it permeated our division there. Anyway, enough of that. Now that gives me time to figure out, okay, I got this to work. So I really have no conflict of interest statement other than to say I'm the poor substitute for Giselle, who really sends her regrets for not being able to attend. And Pat, again, if I get overly excited, please do something to reel me in and stop me, okay? All right, so these are the things that Giselle wanted me to cover in this talk. The first was basically to give an update about BCC's consortium, because it's, spoiler alert, it's moving to Penn State, and I am over the moon about that. Then I'll give you an update about our DFMO program, and I do apologize if I say DMSO instead of DFMO, but here's a little fact. DSMO is the preservative we use to preserve stem cells, hematopoietic stem cells, so I'm always used to saying DSMO, not necessarily DFMO, so sorry about that. And then I'm going to talk a little bit about our precision medicine program, which was touched on in the previous two talks, and actually a parent brought up a very good question, like, why aren't we doing this for everyone? And I agree, it should be done for everyone. Then I'm just going to give you a quick overviews of our two protocols that we currently have open, but recently opened, that I think are very exciting. So first of all, Beat Childhood Cancer Research Consortium, which I'm just going to call BCC now for brevity. It is a very large conglomeration of institutions across the United States and North America. And I'm sorry if the print is really small, but it lists all of them there. And the headquarters for BCC, until very, very recently, was in North Carolina at Atrium. But, as I said, spoiler alert, it's moving to Penn State Hershey. So we're very excited to partner with BCC. So Dr. Schuller is going to be moving to our institution and will be our division chief, but she's bringing BCC with her. So this is a slide to remind me that it takes a village, it takes a village to run a consortium like this, and the names that are listed here, which I can barely see because I'm too old to focus on the confidence monitor here, but Giselle, obviously, oh, thank you. Giselle's, he just made it bigger. Giselle is our fearless leader. The clinical program director is Genevieve Bergendahl. Our program manager is Abby Moore, and there's a host of other people that make this consortium run the way it runs. And how many in the room have interacted with BCC? Before I go any further. Okay, we got a couple. That's cool. So what is BCC, other than this collection of organizations across North America? Well, I think of it really as we have two major focuses. The one focus is development of clinical trials, and specifically developing novel therapies and testing those novel therapies through clinical trials for patients that have difficult to treat relapsed and refractory pediatric or childhood cancers. The other big piece of what drives us in BCC is precision medicine, which is a little bit what was alluded to one of the questions at the previous talk before the break. And so we are so ingrained in giving a tumor a name, giving it the diagnosis, either based on location of that tumor or what it looks like under the microscope. We call that morphology. But we're learning more and more that if we classify those tumors or treat those tumors based on the molecular interrogation, so not just what the genetic alterations are, but what are the protein alterations, expression levels, what's going on in the tumor microenvironment. If we take that approach to the treatment of the individual, we will probably be more successful in treating that patient. That's sort of the ultimate goal. And, you know, when I first, so I'm really old. I've been an attending now for over 20 years, good God. When I first heard of this, 15 years ago, 10 years ago at AACR meetings, American Association of Cancer Research, it was really like a pipe dream. And to see this evolve so much over the past 20 years where we're doing this, it's phenomenal. And it will change the face of the outcomes for not just pediatric cancer, but adult cancers too. That's just an editorial. That's just Val's opinion. So one of the major efforts for BCC has been focusing on DFMO. And here is a laundry list of what those efforts have looked like. It started back in 2010. This was even before I joined BCC. It wasn't even called BCC back then. In 2010, there was an initial phase 1 trial using just DFMO alone. And from that very small trial, there are, I should say, long-term survivors from that study who were only treated with DFM alone. Actually, and one of them is about to start college. That led to a series of phase 2 trials, some that have been completed, others that are ongoing, that are listed in the next few bullet points. So, and the one that I will be talking about in the next couple of slides is a phase 2 trial of DFMO that's used as maintenance therapy. And I'll define better what I mean by maintenance therapy. in children with neuroblastoma. We also have a ongoing phase 2 trial with DFMO that's studying dosing. Does dosing matter? And what impact that has of a standard versus high dosing. We also have a phase 2 trial that is combining DFMO with another old-time chemotherapeutic called etoposide, where you get 6 months of etoposide and then with DFMO, and then you get 18 months more of just DFMO as single therapy. We have a study called the PLAN study. I don't know when it became the PLAN study. It was always PEDS plan, but whatever, which has a randomized component to it. And thank God for the speakers yesterday and today, because I don't have to necessarily explain all those terms. But if there's something you don't understand, stop me and ask me, okay? Because I get on a roll and I get excited, so I apologize. So there's a randomized component to that trial where you get standard high-risk neuroblastoma therapy, and then at the time you're to begin what we call that maintenance immunotherapy with retinoic acid, patients are then randomized to receive DFMO during that immunotherapy or not just during that period, but all patients then receive the 2 years of maintenance therapy. That's the PEDS plan. It also had a component that had to do with molecularly guided therapy that was done in the beginning of induction, but we completed that enrollment, and we're still analyzing that portion of the data. So this is the part B of that study. We also just weren't focusing on neuroblastoma because you'll see in a few slides, really you want to look at mechanism and you want to see what there are other tumor types that potentially would be vulnerable to the inhibition that can be caused by DFMO. And one of those tumor types is high-risk medulloblastoma, which is a type of brain tumor that is not easily treated, at least when it's high risk. And if your tumor looks like it would benefit from being treated with DFMO, we do have, it's essentially an expanded access protocol that is available for those who wouldn't qualify for the other studies that we have there. And that one was originally only available at Atrium in Charlotte, but that is now transferring up to us at Penn State. So here's the question. I mean, I remember asking this when I first joined the consortium back 2011, 2012, like, why DFMO, right? We heard a little bit about that from Dr. Goldsmith, but again, I think that it really behooves us to understand the fundamentals first, because if you understand better the fundamentals of normal cell growth development, then you'll be able to understand better the cancer biology. And that gives you better insight to how can you create more targeted therapies and actually even anticipate what would be some of the potential side effects of these targeted agents, because they do have what we call off-target effects, meaning it's affecting cells that are not the cancer cells. And it just gives you insight to the whole picture. And plus, I honest to God think that it's absolutely miraculous that you take a sperm, you take an egg, you put those together, you make one cell, and 9 months later, you end up with what we would call a human, a baby, right? That hopefully has 10 toes, 10 fingers, etc. And the only way that can get accomplished is by a highly regulated program of development. And we've seen things when sometimes that program goes awry. Sometimes a person's born with 6 fingers on a hand, not 5, etc. May not be the end of the world, but that's when the program has gone awry. Because the body has systems where it's going to turn things on, turn things off. That's how you can differentiate, right? Because remember, everything came from one cell that, as we heard earlier, had 2 copies of that DNA program. And that program has to get replicated over and over, and yet genes that are turned on and off have to occur so that you end up with that fully developed person with a relatively fully developed immune system at the end of 9 months. It's really surprising that it doesn't go wrong more often. But our bodies have a lot of checks and balances to counteract when things go wrong, and when and also to make sure it goes correct. And then once you've sort of developed those, then you have to maintain those cells. But you have to have a balance. So I'm an immunologist too, so we call this homeostasis. There's the balance. You want to have a robust, immediate immune response, but then you want it to go back to normal. You don't want it to overshoot and then cause problems. It's all about balance. And that's really what your normal cells are doing. They're going through a balance of having enough nutrients or fuel, we call that the sugars, to simplify it, the energy to make a new cell or perform the functions that it's supposed to, and also provide the building blocks if it's going to build a new cell. It has to have those amino acids, it has to have the nucleic acids to build that new cell. With dormancy, because not all those cells have to be really active or metabolically active all the time. You need a few that are kind of like resting, call me when you need me, you know, kind of thing. And like if something gets injured, these cells will then kick in, they will wake up and start to differentiate and replace whatever it was that needed to take its place. Or like if you're going through puberty, there's a bunch of cells that were laying dormant that will wake up, start a new program, and allow you to develop what we call the secondary sex characteristics that we call puberty. Do you follow all that? So that's sort of the normal, what happens. So now we have a cancer cell, right? And the way I look at this, and this is very simplified and took decades of research to come up with these concepts. But a cancer cell generally requires a lot more fuel or energy to survive, because very often it is dividing more frequently and helping to build new blood vessels so it can get oxygen to survive, because if a cell has oxygen, it actually can produce its fuel more efficiently than just burning off glucose. And it also needs a lot of those building blocks. It needs the supply materials in order to build those new cells. And what it will do is very often it will hijack those normal cell functions to give itself a survival advantage. And so the things I have listed there in the smaller bullet points are examples of that hijacking that can occur. And so sometimes a cancer cell will only use one or two of those mechanisms. Sometimes it uses all of them simultaneously. Sometimes it'll do it in series. But it senses what's going on around in its environment in order to make sure that it has a high enough supply of energy and the building blocks to do its job, which is to build a tumor, which is really not helping the human body as a whole. Okay? And so it can do that by changing the regulation of its cellular metabolism or how it utilizes or generates its energy to meet up with its new energy needs. It can actually even eat parts of itself. It's through a mechanism called autophagy, where it will eat up some of those proteins and recycle the amino acids that make up those proteins to make other proteins that will help to maintain that survival and growth of the cancer cell. Sometimes it can eat itself too much, and it can die that way, and we can leverage that for a treatment. It needs to hijack the way a normal cell or organ will develop blood vessels so that it can make sure that there's a sufficient oxygen supply delivered to the tumor. Sometimes tumors grow so rapidly and they haven't built in those blood vessels that if you were to take that tumor out, it's dead in the middle. It's because it didn't get enough oxygen. It sort of starved itself. And we heard a little bit about this in some of the other talks. The cancer cell can sort of send out parts of itself to migrate to other parts of the body, where I think of it as kind of tilling the soil or preparing the soil in other locations in the body to create metastatic disease. The other way it can hijack the immune system, or the normal function, is to sort of hijack the immune system. And the easiest way I can put this, or one of the most common ways, is making a Harry Potter analogy. And the cancer cell will put an invisibility cloak on itself, and it won't be seen by the immune system. The immune system just passes it by. Or the immune system has seen it so many times, it's like, well, wait, maybe I made a mistake and I'm not supposed to attack this, and lets it go. That's the tumor evasion that was talked about earlier. So if we really understand better all these different mechanisms, then we will be able to develop more effective therapies that can block or reverse these processes and stop these cancer cells from growing, kill those cancer cells, and perhaps even wake up the immune system. All right, everybody still with me? Okay, I see some heads nodding. It's okay to say no. This also concept was a little bit touched on earlier. A cancer tumor is not, the cells that make that up are not all the same. There's heterogeneity in that, innately in that. And just like in a lot of our normal organs, we have cells, they can be referred to as cancer stem cells, that are the ones that are dormant, lying in wait, and if there's a trigger that will wake them up, to then go on and differentiate into a new cancer cell. And that's often a mechanism that causes a relapse. And the reason that those cells survive it is they are just not as vulnerable to being killed off by our conventional or current chemotherapy and radiation treatments. So all right, I'm going to see what this thing does. Is it the spot? Oh, geez. Okay, sorry about it's a spotlight because you can't really see it on here. Well, anyway, the top half of that slide, you give your chemotherapy, you get unspecific killing, and the tumor will shrink. But yet there's one cell, or a population of cells that survive, which is those ones that can undergo self-renewal, and it takes some time, and there can be another trigger that causes that to happen. Then we'll grow up, and in very simple terms, it would be the relapse. However, if you treat the tumor with more targeted therapy and targeting to kill those stem cells off too, then the tumor will shrink and then regresses, and you don't get that relapse. Very, very simple simplification of the whole process. But these are sort of the things, the fundamentals you keep in your mind when you're trying to develop more targeted therapies. So, all right, how does this go back to neuroblastoma? Because I know that's what I'd be asking next. And DFMO. So we heard about ODC, which is an enzyme that promotes cell proliferation and will help to supply the cell of its required nutrients. And ODC is often elevated in high-risk neuroblastoma, and it's been shown that outcomes are worse in patients that have elevated ODC levels. So you can imagine that if we block the ODC with something like DFMO, then it actually will decrease that glycolytic metabolism. So glycolytic means sugar metabolism. That's the fuel. You're helping to cut off the fuel supply. And as we heard earlier, Dr. Goldsmith had talked about how it can influence the milieu of your immune system. Well, it also does another thing at a cellular level that becomes important when we talk about that stemness or that ability to self-renew. And there's a pathway. So remember, normal cells, there's a lot of checks and balances to keep things in place. So there's this thing, it's called the LIN2BA, or LIN228B, and LET7 axis. And if you have that seesaw leaning towards an excess of LIN28B, then you have increased glycolytic activity or increased fuel production and a maintenance of that stem-like properties. But if LET7, sorry, I am failing my eye test big time right now. LET7 is in excess, then it is pushing things so that LIN28B is not as active, so you have decreased fuel production. And a lack of stemness. Well, it turns out that MIC-N helps to push this seesaw towards Lin28B. But if you treat a cell with DFMO, it counteracts that and pushes the seesaw more towards the LET7, which is the direction we want it to go. And that is why we say, yeah, DFMO is great for, high-risk neuroblastoma because of the association with ODC, but you can see that now this drug would probably be effective in other cancer types that are affected by that Lin28B LET7 axis. So it's not just a one-shopper. And again, this is illustrating it's not just all about the morphology. It's really about the molecular makeup of that cell and what makes that cancer cell tick and survive beyond its neighbors, the normal tissues. So this leads me to the discussion of a phase 2 DFMO trial that was really based on, we're really trying to mop up any residual cancer cells after you've been treated and try to eliminate those cancer stem cells that are waiting and being dormant that would pop up in the future, potentially causing those relapses that survived the scorch and burn treatment that all of our high-risk neuroblastoma patients had to go through, okay? So the hypothesis was that if we use DFMO and start treatment at the end of immunotherapy, so again, I'm going to use this thing, it's not really, it's not going to really work, but if they go through what we would say standard of care treatment for high-risk neuroblastoma, and usually then you're done when you finish the immunotherapy with, anti-GG2 antibody, retinoic acid. But instead, what if then, if the patient's in a clinical remission, remember, remission is different than a cure. The definition of remission means we just can't detect it. Does not mean that those cancer cells are not there. That would be a cure, that the cancer cells are no longer there. And the degree that we can say you're in a remission varies cancer type by cancer type, and also as our technology evolves and our ability to detect things, okay? So patients were deemed to be in a remission, and then they could then start to receive DFMO, 750 milligrams twice per meter square, twice a day for 2 years. And the objectives or the outcome of that study was to see if we could improve the event-free survival and the overall survival actually after 2 years. So this was the results of a further analysis of this study, which actually I'm very happy to announce was just accepted by the Journal of Clinical Oncology, so it will be in press soon, but it's just a matter of tying up a few loose ends, but it has been accepted for publication. And the purpose really of this second look at these data was to make a comparison of what our results were from this DFMO study, which is what we call a single-arm study, which meant everyone who enrolled received DFMO, versus a randomized clinical trial where you flip a coin and you decide like what therapy you end up on. Typically, it's usually what's considered standard of care or the most accepted conventional chemotherapy versus whatever your experimental arm or arms are. But as we heard a lot about that yesterday, they can take a very long time to accrue, particularly if it's a rare tumor or subpopulation of patients that you're investigating, like high-risk neuroblastoma. And, our patients can't wait. We can't wait 5-6 years for this to happen. And so you can use other controls for that population that did not get DFMO. In the past, often what we call historical controls were used, where patients that were somewhat treated like the patients that are treated on this study ahead of time before they enroll in this study versus not. And that's an okay way to make a comparison, but it's still not that golden standard of a randomized control trial, which Some would also argue in tumors that are very rare, is that really equipoise? Meaning, is it really ethically fair? Because that, and we don't know if the arm is going to show a benefit or not, but all those patients that were on the randomized arm not to receive it didn't get that benefit, and it's an N of 1 for each individual subject enrolled versus we look at it as the whole study. But for the individual person, that's a big deal. That's a really big deal. So the royal we, not me, but the royal we, was able to work out an agreement with COG so that we were able to obtain the data that were collected on the 032 study, which we heard about yesterday. That was the pivotal anti-GD2 dinutuximab study that did change the outcomes of those patients. So that we could make a fair comparison, because if you just use historical controls, or getting back to the fruit analogy, we heard about apples to, or oranges to oranges, then we heard about oranges to apples, and then oranges to broccoli. Okay, so that meaning they're really divergent. I would say without, initially what we're looking at is sort of oranges to tangelos, because right, tangelos are made from oranges and tangerines. Like, it's not quite as clear as an orange to an orange, but it's certainly not an orange to a broccoli, period, okay? And so the conduct of that, the COG study, that was all done independently of 003B. So there's not any influence in either one of those trials. It's basically making a comparison of those trials. So what happens when we do that? Oh, all right, so first, again, there's always outliers that are enrolled in a trial, and I'm sorry that this is really, really tiny. However, luckily I do remember what the numbers are. But there were originally, I think it was like 140 patients that were enrolled in the DFMO trial, okay, the maintenance trial. And of those 140, actually 87 of them participated on the 032 trial. So that's actually really good, because you know that those patients were all treated the same way, going in, those 87 patients. And there were actually an additional 5 that were treated like they were enrolled on that study, but the study had closed, but the primary oncologist had treated them as if they had enrolled. So they were included in the DFMO treated group. The non-treatment group, which is the 032 group, that actually had a number of patients that were not in a remission at the time when they were randomized to the antibody. And so we wanted to make that a more even comparison. So some patients were excluded from this next type of, were excluded from that analysis. But the bottom line is we still had, 852 patients that were considered to be in the no DFMO arm. So if we do the analysis in terms of event-free survival and overall survival of those that were on the 03B trial, versus those that did not receive DFMO. So the blue curve, DFMO, green curve, not DFMO. And the hash mark with the numbers above it was actually the 4-year event-free mark. So that means these patients, the starting time was the start of DFMO, which had to start like within 30 days of your completion of the 032 therapy. So that's sort of like the starting time. And then if you're on the DFMO arm, you receive DFMO for 2 years. So it really, like, if you just stopped at the 2-year mark, it's like, well, yeah, but what happens to these patients, like, after they're off DFMO, right? So that's why I'm presenting the data here with those marks at the 4-year event-free survival. So that's 4 years after the start of the study. What is the percentage of patients that were event-free, meaning they didn't relapse? And that's the panel that's on your left. And then the panel on the right is overall survival. So that's patients that maybe they did relapse and got another therapy, but are still alive. And you can see there's a difference in those two curves. And that difference between those two curves is statistically significant, both for event-free survival and overall survival. But there were still naysayers or skeptics, and I mean, I appreciate that, because there's bias in this. We're taking a retrospective trial as our randomized, or as our control population, comparing that to the DFMO population. So there's a statistical way, which I believe was recommended to us to do this by the FDA, that has precedent in some adult cancer trials, where you are using a different mechanism to devise that, or analyze, I should say, that control population, and has led to multiple approvals by the FDA for adult cancers. But this approach has not been used per se in the pediatric setting. However, what this is doing, it's called a propensity score match, and the way this is the way I think of it. If you took like all comers, and the data really weren't that different between what we call the no DFMO group and the DFMO group in terms of the demographics, like the age of diagnosis, some of the characteristics of their tumor, like NMIC amplification. In fact, there were more NMIC amplified tumors in the DFMO arm than the 032 arm. But if you were then to sort of subclassify those patients and do a more head-to-head comparison with patients like me, with certain characteristics, then you're kind of eliminating that bias that something was skewed to one end or the other, okay? So this, on the left side, lists the different characteristics that were used to sort of bucket these patients. And you can imagine, the more and more you're bucketing these patients, you're only getting a couple that meet all 12 or 11 criteria that are just like each other. However, we had only 90 patients on the DFMO arm to pair up with those from the no DFMO arm. But we had so many that we could actually take 3 of the no DFMO group and compare that to just one of the DFMO treated patients. And in doing that, that is enriching so that you're just not getting a one-off by just doing one-on-one. You're doing a 3-to-1 comparison. So that was done, and these are the curves. And guess what? I didn't go back and show you that first curve. This is the result of this. I mean, they are practically identical. The only difference is, I think, that, well, I can go back, can't I? Huh. Technology. So, of course, the DFMO curves are going to stay the same because that population didn't change. That's not being affected by the propensity or the pairing. It's the bottom curve. Does it switch the DFMO? Because that's what people were skeptical about, was that, well, if you really do this more head-to-head comparison, then that may wash out that difference between the two curves, but it didn't. It didn't. And it did it with multiple different iterations to look at this, and every time the curves look the same, essentially the same. They're not exactly, if you see it says 73, whoops, but if you go back to the previous one, it was, 74? I don't remember, but essentially it's the same. So what this tells us, and I'm sorry, I went the wrong way, and I think I still am. No, I just went really, yeah, I am. I'm so sorry. Nope. I don't know how I jumped like 20 slides ahead. I guess I got so excited I just started pushing the button. No, it's going why is it only going forward when I push that button? Oh, I see. Val, push the right button and you'll go the right direction. So simple concepts here. All right, I really apologize for this flash show, but there's the rest of the talk. But anyway, all right, so there are the curves. They are still statistically significant, the difference. So what does this mean? These data and this analysis suggests that DFMO-treated patients have half the risk of relapse compared to objectively selected and matched cohorts of external control patients that were from the 032 trial. And I didn't go over what a hazard ratio is because, that's another statistical term that sort of gives me hives. But really, it is saying that you can cut that risk down by half. if you were to give them the 2 years of DFMO, based on these data and this analysis. So this really was is the most robust findings to date that supports the meaningful benefit of DFMO as a maintenance therapy for the treatment of high-risk neuroblastoma following multimodal standard of care. Now, there are still limitations in a single-arm study, and that still can leave some uncertainty about the contribution of DFMO to this observed improved event-free and overall survival. But what you need to do is outweigh the risks of delivering this agent for 2 years. And I took this slide out for the purpose of time, but the profile of DFMO is pretty not toxic, especially compared to what your poor patients have gone through before this, and are manageable and reversible. So you have to weigh the risk of maybe having some of those effects to the potential of an increased overall survival. And so that's why we recommend recommend the incorporation of DFMO and upfront therapy as extended maintenance therapy in high-risk neuroblastoma. And unfortunately, I see that Pat's standing already, which is going to be a problem, because that really meant I covered 2 of the things I was going to cover. But if I can just say, because we've heard a lot about these other things, again, we feel you out there, and BCC is committed that all children, at least at the time of diagnosis and at the time of relapse, will get sequenced. Their tumors will get molecularly interrogated, because there is a definite benefit to that. And I could tell you a personal story about my sister regarding that, but maybe I'll tell you if you want to hear it over lunch. But we can learn so much more if we do this in large numbers. Because, as I said, you know, each tumor is individual, but you do start to see patterns. And I threw this slide up not because it's just pretty, but that middle panel is, you know, hundreds of patients. Each column represents a patient. It's a heat map. And the x-axis going downward is each gene. And it's basically showing a relationship of how overexpressed or underexpressed that particular gene is. But you can see there are patterns that show up, but not everything looks the same, even with the same tumor type. And that's where the individualized or the personalized precision oncology piece of it comes in and becomes important. And we're learning more and more, how can we identify those patients sooner rather than later in terms of how we're treating it. So that is a big initiative that BCC has taken on. And there's also a research aspect to that too, so that we can learn more in the laboratory about those individual patients, particularly those that are not responding as we predict they will, because why? What is different about them? And that is this precision medicine program, which I am now going to just go through slides, because you can I'm more than willing to talk about this. I'm here till tomorrow morning, talk to you about the details of that. The 2 trials that we have open, one is 017. It's a precision medicine and immunotherapy clinical trial. I'm only going to talk about the big 4 pieces of it. The first piece is you have your tumor biopsied, and you have what we call mobilized leukapheresis in order to get peripheral blood stem cells, and also to siphon off these special type of immune cells called dendritic cells, which are these things called antigen-presenting cells, which are the ones that are like presenting like antigen, which is a piece of a protein, to the rest of the immune system to say, hey, I found this. Like, I just gobbled up this piece like a virus. I'm popping this out on the cell surface. Maybe you should go find cells that are infected with this too and go kill it. Well, you can do that by loading those dendritic cells with the tumor RNA and basically forcing those dendritic cells, you know, if you're a James Bond fan, like this would be M, right, his boss, James Bond's boss. So M is gathering this information. She's presenting it to 007, to James Bond, who are the killer T cells, and say, okay, now go, here's your mission, go and find them and kill them. So that's sort of the part 4, the immunotherapy part. But that takes time to manufacture those individually in the laboratory. So in the meantime, we've taken a piece of your tumor, we've sequenced your tumor, we've given you a round of, quote, like standard therapy to hold you off, because we know these tumors aren't going away for anyone. And then we give you cycles of the molecular guided therapy while we're waiting for the manufacturing of the vaccine. And then we end up hitting it again with hedging our bets, collecting T cells after they've seen the vaccine, because you think that you've skewed your T cell repertoire towards killing the tumor. And you're just enriching your immune system to have one purpose: go and kill any tumors. So that's, in a nutshell, this trial. And it's eligible, there's one arm for a brain tumor called DIPG that's newly diagnosed, and then this is the one you want to listen for, is a refractory or relapsed neuroblastoma patients. And some patients have already enrolled in this trial. There's more logistics to it. I'm not going to get into those. But there are a few patients that have enrolled, and again, this will take some time to do. The other trial, this will take 2 seconds, is 018, which is basically a phase 2 trial. It's an upfront neuroblastoma trial that's looking at the anti-GD2 antibody naxitamab being added to a backbone of standard induction therapy, a la like a trial that we heard about yesterday that actually is still in the works through COG, but using dinutuximab up front. This one uses naxitamab up front, and it is open and is enrolling. It's being open at more and more BCC sites, so it's not at all, 60-plus sites, but it is open and enrolling, and it's really looking to see if we can improve the outcomes. So can we make a PR be a CR, partial response to a complete response, like at the end of that first block of therapy, induction therapy? And if patients are then, after consolidation, they could actually enroll to receive DFMO2 as a separate trial. But this is ongoing, and so perhaps maybe next year we'll have info. So that was it. I know, you're getting anxious over there. I'm
Well,
really sorry.
Yeah, I don't mean to
No.
rush. It's just our next speaker has
Yep.
to leave very soon.
Okay, so, and there's our acknowledgements. Again, it takes a village to do this, but the one group that I need to highlight are the patients and the families, because without your generosity for allowing your patients, your sons and daughters, to participate in these studies, we couldn't get anywhere. And that, I can't even say that enough, how much I appreciate that. It does make a difference, so thank you very much.